In this video, I will talk about best practices when you download or work with any large language model. Before working with a model, it's a common and recommended practice to inspect its configuration. A model's configuration contains valuable details about its architecture, such as the number of layers, hidden dimensions, attention heads, vocabulary size, and more. Understanding this information helps you estimate the compute resources required, such as the number of GPU you want. Choose appropriate model serving strategies like quantization or batching, and plan for performance optimization, for example, layer-wise parallelism or model sharding. Before we start this coding, you have to change the runtime to use the GPU that's available in Google Colab runtime, T4 GPU. Then let's install the required libraries. It may take some time. Then this piece of code to free the memory after we finish working with the model. And this is the code to print the configuration of the model. As you can see here, model.config, and the model that I'm using here is qwen from Hugging Face. And this is the way how you can use it from the Hugging Face. So here the config hidden size, this is the size of the hidden layers, and config num hidden layers, this is the number of transformer blocks. Config.num attention heads, this is the number of attention heads. And config.intermediate underscore size, this is the size of the MLP intermediate layer. And here are the tokenizer parameters. For example, config.vocab size, this is the size of the vocabulary. And the maximum position embeddings, this is the maximum sequence length. And then we are printing the model size. And let's have a break until this finishes. So after this cell finished the processing, as you can see here, the model configuration parameters, the architecture parameters, the hidden size is 896, number of layers 24, and the tokenizer parameters, this is the vocabulary size, the maximum position embeddings. All of this is important because it helps you to decide the what would be the GPU that you need for your use case, and other settings that depends on your work. Now let's walk through how we can execute large language model generation step by step. So in this section, I will take you behind the scene of how a large language model generates tokens step by step. I believe the most effective way to understand the performance challenges of large language model serving is through hands-on incremental execution, observing how tokens are generated one at a time. And I will use the same model, qwen model. So to get started easily, let's run the qwen 2.5 model using the Hugging Face pipeline library. So I will run this cell. This code loads the qwen.5 model and generates text using generator prompt. For the input prompt, I used write a short introduction about US capital city. And as you can see, this is the response. Write a short introduction about US capital city. This is the generated text. Washington, D.C. is the capital city of the United States. And now let's implement qwen token generation token by token. So step 1, we will specify the model and load tokenizer and model. As you can see here, we specify the model, and this is the tokenizer from the Hugging Face. And then we define the input prompt, the text about communication history here. And the step 3 is convert tokenize prompt, or let's say to tokenize the prompt to the input format that model understands. We are using here the return tensor PT because this is the format that the model understands. Then this is the main generation loop to generate tokens one by one. So here set the current context for generation. And here generate predictions, which is the token candidates for next token. And then we get the logits, and the logits are the raw prediction scores. It means without the probability for each token predictions. Then we select the next token from the predictions generated in step B. Here, select only the logits for the last token. That's why we are using here -1, because we want the last token. And convert the logits to probabilities using softmax. And then we do some sampling for the next token from the probability distribution by using this multinomial method from Torch. And then to print the next token and to calculate the time. Here we are tracking the time spent in token generation. And finally, we append the new token to the input sequence. And then to check if end of sequence token was generated, which is the EOS, to stop the processing. Then finally, we decode the entire generated sequence by using tokenizer.decode. Let's see here. Next token is how. Then the time taken for generating the first token is this 0.16 seconds. And then the next token is will, and this is the time taken. As we can see, the time here is less than here. Then as you can see, the time is going down. So let's see the prompt again. What was the prompt? The history of human communication is a story of innovation from ancient cave. How might the next wave of communication tools shape our relationships, societies, and sense of identity? So this is the response from the model. So this is generation completed, the end of token reached. So here, this is the last token, which is here this is here empty, nothing. So the total time take for next token was 3 seconds, about 3 seconds. The history of human communication is a story of innovation. So this is the total time taken to generate token by token. And in addition to demonstrating the code, I'll track the latency of each token. Let's run the cell. during the generation process. So the demo here generated 35 token. And as you can see here, the first token takes the highest time, then the time reduces. So the average time is about 0.09, about almost 1, the average. As you can see, this is the average time. As machine learning engineers, we can quickly recognize the inefficiency. The model recomputes attention for all previous tokens each time a new token is generated. This repetitive computation over known tokens is costly and unnecessary. We can avoid recalculating the same attention for previous tokens and instead focus computation on the newly generated one by using the key value cache. The key value cache does this optimization stores the attention keys and values computed at each layer for previously generated token, allowing the model to skip redundant computations during decoding. The key value cache shifts the large language model calculation from full sequence recomputation to an incremental cache augmented workflow, trading increased memory usage for significant compute savings. This technique dramatically reduces redundant computation and enables much faster token generation. Let's have a look at the code. Here we are using the same model, qwen, and the same prompt. And then the first token generated to be false. And here to use the tokenizer to have the format of the input that the model will understand. Here we are defining the key value cache for faster generation by these pieces of code, passed key values to set to be none. Then this is the for loop, print the size of the input, and then to stop gradient. Here the outputs of the model, and this line of code to use key value cache from previous iteration. As you can see here, we are storing the pass key values in the variable pass key values. Here to use the cache to be true to enable the key value caching, and the maximum new token to be 100 and minimum new token to 100. And this is the logits, the output of the model, the raw output without the probabilities. Then to update the key value cache by outputs.past key values. And here to set the coda to be synchronized. And this is the last token as we did previously. And here to use softmax to get the probability of the logits and to sample instead of argmax by multinomial. Then to update the input IDs with only the new token using the key value cache. As you can see here, we are generated token ID, not concatenating with previous tokens because we are using the key value cache. Then to print the next token and to calculate the time. Let's see the output compared to the example one. So this is the input size with a shape with 1 and 225. And this is the next token, let. And here this, the second is less than before. It's 0.1. Previously, I think it was 0.16. And the input size now 1 and 1. Then this is the token generated. As you can see, the time is going down. Let's see the total time. So it's a big difference. Actually, here it is 0.02, but previously it was, let's see, it was 3 seconds. So we saved a lot of time, which is very important. And let's plot it. This is the comparison between using without using the cache, and here by using the key value cache.